She is so very nicely quoted by Edmund. Today we are overwhelmed with such a great positive personality with us, Mrs. Swapnil Srivastava ma'am, who is Principal Technical Officer in Big Data Analytics Group, CDAC Bangalore. On behalf of each and every member of DYPCOE, I heartily welcome you, ma'am. I would like to take this opportunity to introduce Swapnil ma'am. Ma'am has 20 plus years of experience of technological research and managerial experience. She is presently working as Principal Technical Officer in Big Data Analytics Group at CDAC Bangalore. She has effectively contributed toward research projects, mission mode projects, turnkey projects, and technical consultancy for clients ranging from UIDAI, EPFO, BEL, RGUHS, SET India, and international agencies. She has few international publications to her credit. She has also contributed in various courses and workshops. She is pursuing her PhD in the area of big data security and privacy from IIT Bangalore. Now, I would like to invite Swapnil ma'am to address the audience on the topic deep learning in big data analytics, techniques, application, and challenges. Over to you, Swapnil ma'am.
Yeah, thank you, ma'am. Thank you so much for such a warm welcome. And good afternoon, everyone. So the session is scheduled post lunch, and I hope I'll try to keep it interesting. Uh, I would. I would like to know about your awareness in the area of big data analytics. Maybe with the raise of hand, you can say you can just respond that how many of you are aware of it, have worked in big data. Oh, great. Okay. Nice. And deep learning? Okay, great. Fine. So let me start the session. Okay, and let me just remove the video. Okay. Okay, so this is a topic that I would be talking about today. That is deep learning in big data analytics techniques, applications, and challenges. Now, I have some experience in the area of big data analytics, and I would be talking about the application of deep learning in this area. So this is the agenda. I have tried to keep it, I have tried to keep it both theoretical and hands-on because it's difficult to just, show the code without knowing the concept. So we'll first talk about, what is the need for deep learning for big data, and what is deep learning, and convergence of AI and big data. And deep learning per se, it has various substreams. It can be used for supervised learning. It can be used for unsupervised learning. We will be focusing more on the supervised learning aspect in this session. And then we will briefly will try to understand what are the different types of neural networks that comprises that the deep learning stream comprises of. So we have standard neural networks, convolutional neural network, recurrent neural network. We'll see a few examples, and then we will see the contemporary and emerging applications of deep learning in big data, and what are the challenges which needs to be addressed for the seamless implementation of such applications. So just to start with, what is big data? Maybe for those who are not conversant with this area, but I'm sure you all would have heard of big data. And so, okay. Now, the big data, just a minute, why is it not? Okay, let me show this slide in a different manner because the text is not visible. So, what is big data? Uh, the this term big data, basically it got coined by the scientific communities like astronomy and genomics. They are the ones who came up with this term big data, and they coined this term to express their experience that they observed in 2000. These communities, they observed huge data explosion in the year 2000s, and in the early 2000s, and they couldn't, the problem they faced was that a lot of data was getting generated, but the existing tools were not able to process and analyze this data. So So what was they were not able to analyze and process the data. Big data, and soon other domains also started facing the similar experiences. They also started observing the similar phenomena. Big data, as such, it doesn't have any single definition. It is. It is in the year 2011 in the Meta Group report. What the people who composed that report, they came up with various data management issues that were faced by the e-commerce companies then, and they modeled these issues or the limitations with respect to three dimensions, which are volume, variety, and velocity. And they also gave certain solutions. And a year later, Gartner came up with a definition of big data, which is big data is high volume, velocity, and variety information assets that demand cost-effective, innovative forms of information processing for enhanced insights and decision making. So there is data which is of high volume. It's coming at a different velocity, and there are different varieties of data which are getting generated. So there is a need for a cost-effective analytics and processing techniques in order to generate or come up with or find certain insights for decision making. People articulated different definitions of big data from different perspectives. Some even said that the three V's are not sufficient. Big data cannot be defined by just three V's. So there came veracity, value, variability, and more. So, what is big data analytics? Okay. So, big data analytics are emergence, as we said, the existing or the traditional processing and analytic solutions, they fail to process and analyze the big data. So, big data analytics are new types of or the novel processing and analytics techniques which enabled analysis of variety of data being generated from at different speed, and a huge volume of data. So, and since the conventional BI solutions, they couldn't analyze, so there were many big data analytics initiatives that were made in 2000 and also in the current decade. So some of them are the Google came up with the Google file system to store the data generated by the search engine. Google mapped different applications. The HDFS, that is Hadoop distributed file system, it is the open source implementation of Google file system. The internet, various internet service provider giants like Amazon or Google, they came up with their own NoSQL databases like Google Bigtable, Amazon Dynamo. So these were the tools and techniques that were developed for storing big data analytics and in a way scalable processing of and analysis of big data analytics. Okay. So such solutions resulted in various applications, development of various big data analytics applications. So the crux here is the things that we cannot observe at small scale. It can be uh, extracted, or it can be viewed at a larger scale. So what we cannot get from sample data, the kind of inferences, like unprecedented inferences that we can derive from big data. And using various big data analytics solutions, here are the few applications, big data analytics applications. One is recommender system. So it is, you would definitely would have seen this recommender system in Amazon e-commerce portal. So if we want to order a book or any product per se, if you scroll down, the web page will show that the people who purchased a certain uh, product that we are looking for, they also purchase they will give the recommend that they also purchase so and so product along with this product. So these are the recommender systems which are in place. And they are built from the transaction data or the sales data which is there at the back end. For flu detection, Google came up with a flu detection algorithm. So what they did is they collected the search engine keywords and they came up with a model. And what they did is they came up with a predictive model which found the frequency of searches, the search keywords typed by different end users, and they predicted these frequency, or they came up with the model with respect to these frequencies and the various regions, or we can say with respect to time and location. So what they did is they tried to find which all location and at what time such keywords were typed, or these keywords were executed by the end user using the Google search engine. So they come with a predictive model, and the result they got from the predictive model, it actually matched the result of the Center for Disease Control Department. But the difference here is that the Google generated the same records, or the same, they came up with the same figures using the keywords in real time. Whereas CDC, it took a very long time because they collected the data from various hospitals to generate such a report. So if we look at the big data analytics application here, this flu detection application, it actually reduced the time of generating the insights, and it actually helped the authorities to take the timely actions. So the recommender system is like generating unprecedented or novel insights for the end users. Flu detection here, the big data was used for, the societal cause in the interest of the society. Then here is an example of proactive tiring. Again, one more big data analytics applications for the cloud service providers. So what was done here is, we all know that the service providers who offer the services at a very low cost, they have tight budget. So what they have to do is they have to plan the resources in an optimized manner, so that the efficiency of the service provided by them is not compromised, and also the solution is a cost-effective solution. So here, this is the proactive tiring solution that is built for the information lifecycle management for a cloud service provider. So what is done here is, what proactive tiring does is, it takes the performance data, which is stored in various logs. So the performance monitoring data, the log data, all these data, they are the input to a predictive model. And what is predicted is the future load. What is the load or the storage load which is anticipated, say for a few hours or a day, and this would help in proactive tiring. So before the service provider reaches a certain situation, they can take certain proactive actions, like they can up tire the storage volumes which are in lower tires, and they can down tire to free some of the storage volumes which are kept in the end user devices. And this shuffling can be done based on the anticipated storage IO load, which has been generated from uh, the predictive model based on the performance logs. Okay. So here are certain applications we saw, and these applications basically they are based on uh, the alphanumeric data, or we can say the structured, or to some extent the semi-structured data. Okay. Now, this is the current big data technology landscape. So, though the big data community started off with Hadoop ecosystem, but now there is Spark. There are different visualization tools. There are different analytics tools. And the big data now, it is not that the big data is in the custody of few, internet giants. Now, the big data is being generated today by various public and private organizations, and they have their own domain-specific requirements, and based on their requirements, they can use any of these technologies depending upon their domain and the requirements, and build a data-driven application. So this is the big data trend. Okay. So it was anticipated sometime in 2050 that 90% of the world's data was created in the last 2 years. Yes, data is being generated uh, at an unprecedented speed. Okay. And it was also predicted, or that uh, from 2010 to 2020 there is going to be 50 times growth of the data, and this data is going to be mostly sensor data, device data, or social media data, in addition to the conventional transactional data, or what we call as the enterprise data. Okay. And it was also felt that 80% of the data that is generated is the unstructured data. So it is basically machine data, or the social media data. So we have most of the data, big data, is unstructured data. Now, the unstructured, we understand the difference, right? Structured data, where there is a metadata associated with the data. Whereas in unstructured data, there is a lack of such metadata. So it's very difficult to analyze such a data in absence of the metadata. But it doesn't mean that such unstructured data doesn't have any value. It has the value. And there is a need for algorithms to analyze the process and analyze the unstructured data, which forms the major chunk of the big data. Okay, so the solutions that we saw, be it Google flu detection, they were all mostly, they were based on the enterprise data. Okay, be it cloud service providers proactive tiering or be it recommender system, it was based on the enterprise data. But what about this unstructured data, which is also could be the enterprise data, but uh, but we need to analyze and process them as well. Okay. So such a requirement, to analyze huge amount of data, structured data, or analyze the interpret unstructured data is what resulted in the resurgence of neural networks in the big data era. Okay, so neural networks, you all would have heard of this term. We all have heard of this term. Neural network, one of the machine learning technique we heard of for classification. Artificial neural network is what it was called. And but it seems that now we mostly talk about deep learning. Okay, so what is this deep learning? So if you see this chart here and why the resurgence of neural network, the traditional machine learning algorithms, they were built not for big data, they were built for sample data. Okay, and any algorithm which is based on or it is developed on sample data, that may not be used in the real world scenario, or it may not give the required performance in the real world scenario. So such algorithms, which are built on sample data, they uh, they fail to generate the business value or the economic value which is required at a very large scale. Okay, so they fail to give such a real world generate such a real world value. So, but there is huge amount of data. Okay, so even if the amount of data is increasing, the performance of these traditional machine learning algorithm, it plateaus after a certain time. Uh, then came the shallow neural networks, or we can say artificial neural networks. Okay, yeah, they also, they show the performance improvement to a certain point, and then they also plateau down. Okay, so what is observed here is as the amount of data is increasing, okay, and as the layers of neural network is also increasing. So as we increase the neural network size and the data also, the training data is also increasing, the accuracy of prediction, sorry, I don't know, one minute. The accuracy of prediction is also increasing. Okay, so that is the reason. So basically what we can say is deep learning is helping in a kind of coming up with big data analytics products, which can be used in real world scenario, which can generate the business value for various organizations, which the traditional machine learning algorithms failed to do. Okay. Now, how we can come up with such big algorithms? How can we build such huge layers? The deep neural networks with so many layers. Okay, because there has been a lot of development in hardware. Okay, we hear of GPUs, the network bandwidth or the network configuration has also improved. The data size definitely has improved, and the algorithms have also improved. And any deep learning technique, what or when we want to apply deep learning technique, we should have an idea. Okay, so these are the three steps: idea, code the deep learning, experiment. Okay, and see whether you are getting the desired output for the idea. Okay. In absence of the hardware growth or the development that we saw, or the in absence of the introduction of various, or we can say the improvement in deep learning algorithms, this cycle would have taken a very long time. A code experiment, maybe days for that particular neural network to get trained. But with the development in the advancements in the hardware technology, networking technology, the algorithms, like instead of sigmoid, there is the ReLU activation function, which helps in faster training of the algorithms. This cycle or the time for execution of this cycle has also reduced. Okay, so and that is what is required in today's business scenario, the faster generation of insights. Okay, so that these are the reasons which have resulted in the resurgence of neural networks in the big data era. Okay, so what is deep learning? Though we heard of artificial neural network, but the term deep learning, it popped up in the year 2006, and it has emerged as a new area of machine learning research. And most of the deep learning models, they have their roots in artificial neural networks. And why do we call it as deep learning? The artificial neural network is shallow. It will not it comprises of few layers, one or few layers, hidden layers. Whereas in deep learning, it's called deep because there are a lot of multiple layers are used in the network. There will be multiple hidden layers in addition to the input and output layer in the deep learning uh, techniques. So this is the one of the definitions of deep learning. So it is a new area of machine learning research which has been introduced with the objective of moving machine learning closer to one of its original goal. Okay, so machine learning falls under artificial intelligence, and the deep learning is about learning multiple levels of representation and abstractions that helps to make sense of data such as image, sound, and text, which are nothing but the unstructured data. So deep learning, the recent developments or the developments over the uh, past few decades in the area of deep learning has been basically to process and analyze the unstructured data. So let us we in the deep learning definition we see machine learning is also mentioned. Then we also see the term artificial intelligence. So what is the relationship between these terms? Okay, so the artificial intelligence. So what is artificial intelligence? It is it is to make the computer think like humans. Okay, so what all techniques, algorithms that you will use, or the models you will use to make a computer think like a human. Okay. Machine learning, if you see here, artificial intelligence, machine learning, and deep learning, they're like, concentric circles. So machine learning is a subset of artificial intelligence, and deep learning is the subset of machine learning. So machine learning, basically, it is the set of algorithms which derive patterns or insights from data. Okay? So the machine learning algorithms are the is a substream of AI. So AI can be done with data, it can be done without data. So machine learning is the substream where we are deriving patterns or generating intelligence from data. And Deep learning is a subset of machine learning, which comprises of algorithms which generate, or derive patterns using neural networks. Okay, this is one of the substreams for the techniques for machine learning, and deep learning is based on the neural network substream or technique of machine learning. Okay, so I hope this makes it clear. And now coming with the convergence of AI and big data. So as I said, the earlier AI algorithms or the machine learning algorithms, they were developed for sample data. Okay, so they didn't give the kind of performance or the accuracy which was required for their real world implementation. And it's the big data. So what what we can say is uh, the way the telescope comprehends the universe, and the way we can make use of the microscope to study the germs. Big data helps us to, derive the novel insights, which we can definitely, we can appreciate how search engine keywords can be used for flu detection. We couldn't have thought of any such applications prior to big data. Proactive tiring. So these are the applications that we have started appreciating. So so to process this big data, there has been a lot of advancements. There have been a lot of progress in AI. We can say there has been a new era of AI, or we can say that is what we call as the contemporary AI. So the contemporary AI is or the development in the field of AI has been because of the big data. So the big data has enabled, or you can say catalyzed, or you can say inspired the AI communities to come up with the algorithms which can derive accurate insights from the big data, and which can be used in the production mode by various business organizations. And what we can even say is that it's a kind of give and take. It's a mutualistic relationship between AI and big data. So AI has kind of that we have seen very different advancements in AI or the new set of algorithms because the big data was available, and we could derive novel insights from big data, or unprecedented application of big data because of AI. So it's like it's a mutualistic relationship between AI and big data. So they are growing hand in hand, right? So as I said, so the need for deep learning in big data analytics is to derive insights, accurate insights from the big data. So that is why deep learning is used in big data analytics, and deep learning is a sub stream of AI, and to derive insights for unstructured data, basically. Supervised learning. What is supervised learning? So, supervised learning is we already know we have a set of input and output. Okay, so we know for the given input X there is going to be an output Y. Okay, so what is done here is a mathematical model is built that maps these set of inputs to desired output Y. Okay. So supervised learning, basically it is a two-step process. First is the learning step. So the learning step is coming up with this mathematical model which takes the input set X and the output set Y and builds that mathematical model. And the evaluation step is when the model is used. So what is the input X is fed into the model, and what it gives is the predicted output. Okay, so these are the two steps of supervised learning, learning and evaluation. And to make it uh, clear, here is an example. So we have this training set. Okay, so TID, transaction ID, we may not consider. There are the input to this learning model would be homeowner, marital status, annual income. So these are the inputs. And what we want to know is, a person with these attributes, whether he will be or he or she would be a defaulted borrower or not. Okay, so this is what we want to know. So we already have a set of data. We already have the set of data which we call as training set, where we know the input as well as the corresponding output. So this training set is so the learning is the input to the learning algorithm. So these algorithm, it will learn the model and from this data, and will come up with a mathematical model. So there will be a mathematical representation of the pattern which is there in this training set. Okay. So this is the learning step. Now there is going to be an evaluation step, where say, we model it as a decision tree. The mathematical model here is a decision tree. So this mathematical model uh, is a decision tree, and now we apply it on the test data. Okay, so you can have a look, you can check this for transaction ID 11. Is the homeowner? No, right? So what will happen is, we'll traverse down the right subtree of homeowner. Okay, marital status is married, so we'll further go down the right subtree of marital status, and what we get is defaulted as no. So the label here, which is unknown, or the y, which is unknown, so we can predict here that the homeowner, I mean, a person who is not a homeowner, married, would have a defaulted borrower value as no. So it won't be a defaulted borrower. And similarly, it could be found for the other attributes by applying, or by traversing this decision tree, by choosing or applying these values in the decision tree till we reach the leaf node, and that leaf node value is going to be the predicted value of the output, that is y. Okay. Right. So here is one simple linear regression example. Okay. So what we have here is there is a sample data here. Okay. So there are the sample data has 42 records in it. Okay. And the attributes are house age, what is the size, and the market value. Okay. So what the simple we are applying the simple linear regression here is, the x would be the area, and we want to predict the market value. Okay. So the first step here would be to plot this market size with respect to market value, and what we get is this scatter plot, which shows that as the area increases, the market value also increases of the house. Okay? But this is this is a kind of an observation that we can make out from the scatter chart, but we cannot make any prediction. So to make any prediction, we need a mathematical model. Okay. So to get a mathematical model or the regression model, we'll have to apply the learning step. Okay. So from this data, the a mathematical function, will derive a mathematical function which represents this data. Okay. So this is the code. Okay. So the linear regression is applied, Okay, and we get this line. So what we get, the mathematical function or the model here is this line function, okay, which could be used for making the predictions. Okay. So this is the mathematical function, which is a line function. So the market value is this is the intercept. It's like a plus, or we can ax plus b. So we have b is 32,673 and 35.036 square into the area, that is the square feet. Okay, so this is the mathematical function, and we can make use of this function to make the prediction, and that is what is done in the evaluation step. So you get some house of some, say, square foot area. So you substitute the size of that house in this function, and what you get is the predicted market value. Okay. So this is the code which is used for market we can say the prediction of the market value. Read this. Okay, predict. So we have, what we have done is, for prediction we have different square feet. We have kept it in a file. Okay, and for these different square feet, so we can say this is our test data. We want to make the predictions. Okay, so the model, that is the reg model, which has been developed here. Okay, so we read the data file here in the learning step, come up with a linear regression model. Okay, and now this model we are going to use to make the prediction. So what it will take is, it will take all these values, okay, and it is going to generate the corresponding market price. So take these value, apply this function, and generate the corresponding market price. Okay, and so this M price will be the set of, or these collection of these market price. And then okay, so now this is something related to Python. We are going to add this also to the data frame, so that we get the area as well as the predicted market price, and we can store this in a CSV. Okay, so the crux here is how we can predict. So here we have applied the linear regression to make the predictions. Okay. Now, how this linear regression model can be implemented using a neural network? Okay, so to implement this simple linear regression, it can be implemented using a single neuron. Okay, so what is fed here is the area. So the input is the area, and this is a neuron. Okay, and what we get is the market value. Okay, so what is done here is so area. Okay, which is nothing but the value of x here. So substitute x with the input area. So we'll get some value z, which is the market value. And then an activation function would be applied in this neuron on that market value, the market value that we have got. Why so? Because if we if we consider the simple linear regression, okay, if we consider this, this may go down, okay, and at some point, say for the area 700, some area says 700 square feet, it would touch 0, and it may, below 700 square feet, the market price value that we would get would be negative. Okay, which doesn't happen, which is never the case, where for a price the market value or for a particular area the market value is negative. Okay, so that is what is taken care of by this activation function, which is called the ReLU function, rectified linear unit. So what it does is, as soon as this linear function or this line touches 0, any value of area, prior to it or less than this, the value at this particular point, the market value would be taken as 0. It would be taken as 0 and not any negative value. Okay, so that is what the rectified linear unit does, ReLU. Okay, So you will so this particular area, it will you will apply it in this linear function, get the market value, and this market value will be max after applying value. It is going to be the max of 0 or z. Okay, so it will, you will get z as long as this market value doesn't touch the or the market value is not 0. It doesn't intercept this x-axis. Okay, till that point, your the you will take the value of what you get from the equation, else it is going to be 0. It is not going to take the negative value. Okay, so the input here is the area of the house. The neuron here would compute the linear function and take a max of 0 using rectified linear unit, which is an activation function, and the output is going to be the estimated market value. So what this activation function does is, like, it will let us know whether so if the value is greater than 0, then we say this neuron is activated or it is active. Okay, so that is what the activation function helps in when we have different layers of neural network. So this is the linear regression, which can be represented as with single neuron, but we can have other applications or the for supervised learning, where we will, what we'll do is we'll stack these neurons in, or the neurons are stacked in different layers, and now we are going to see such applications. Okay, so neural network. Okay, so the neural network term, it was the inventor of the first neurocomputer, Dr. Robert H. Nielsen. He defined neural network as a computing system made up of a number of simple, highly interconnected processing elements which process information by their dynamic state response to external input. Neural networks, they are created by human brains. You know how the human brain processes the data. Okay, so this is what is that is what the neural networks are inspired from. So the human brain, is made up of billions of neurons. We saw one neuron, and it is made up of billions of neurons, and they are connected. Okay, these neurons are connected with each other, and it's the dendrites, okay, which accept the input. Now the brain will get the inputs from the sensory organs. Okay, let us take the example of a child. A child, when we get these alphabet books for the child, okay, and we teach them A for apple. Okay, so what are we doing? The child from its eye would see the apple, okay, and it doesn't know that this is apple. Okay, so we keep on training the child, this is an apple, this is an apple. So the input is from the eye, and the mapping is done in the brain, okay, with the help of neurons. Okay, this is an apple. Okay, and later whenever the child sees the apple, the set of neurons, which have mapped the visual apple to the word apple, would be triggered in the child's mind. We don't know where in the brain. Okay, and the child would recognize, okay, this is an apple. Okay, so that ability of the brain is kind of been simulated by neural networks. Okay, so the neurons here are nothing but like the neuron cell in our brain, and they are connected with each other. So this is the representation of human brain in terms of neural network. So say there are three inputs, x1, x2, x3. Okay, and we want to perform some kind of operation on it. So now there will be weights associated with these x1, x2, x3 inputs. So x comprises of three inputs, three variables, x1, x2, x3, and we have the output y. Okay, so we know what are these x1, x2, x3, and what is the corresponding y. Okay, in the supervised learning, we know what is x1, x2, x3, and what is y, right? So similarly, let us take the child's example. So we know that, these are the, so apple is red, we know the shape of the apple, it's a fruit. So we know all these characteristics, and we know that, okay, hence it is called apple. Okay, and that is the output, that it's an apple. So when we want to use the neural networks, okay, so the characteristics of apple will be the input, and the output is going to be the y. So these characteristics are nothing but either, from the image, or in the case of human, what we see. Okay, so we see these characteristics and we make the prediction. So in case of the neural networks, you have this input, and there are weights associated with this input, and there is a biasness. Okay, now we know the input, we know the output, and this is what the neural, in between these weights and biases, is what the neural network needs to figure out. It needs to figure out these values, which will give, for the given input with characteristics x1, x2, x3, it would give the correct predicted output y. Okay, so this is what the neural network would need to figure out. Okay, and that is what happens in the human brain. Okay, even in the child, we don't know how, but the mind makes such a map that whenever the child would see an apple, and based on the initial training that the child has got, the child knows that this is an apple. Okay, so here we saw this one neuron, okay, but a neural network is made up of multiple layers, and each layer can have several neurons stacked in that layer. Okay, so the key principles of deep learning here are that this is a multi-layer structure. Okay, so a neural network is a multi-layer structure. These are the yellow ones. This multi-layer structure has three types of layers: the input layer, the hidden layers, and the output layer. Okay, so so input layer is X, and the output layer is Y. Okay, and it depends upon the number of neurons depends upon the input size in the input layer, and whether it is just a binary prediction 1 or 0, or is it just a numeric value. Then in the output layer we'll have one neuron, but in case of multi-class classification, there will be multiple neurons will be there in the output. Okay, and these red ones are the neurons. These are the we will say four hidden layers. Okay, and each layer here we can see that there are four neurons in these layers. Okay, and this is called the densely connected neural network, because each neuron is connected to the corresponding, or we can say the neurons in the previous layers as well as the neuron in the subsequent layer. Okay. So this is the structure of the neural networks in deep learning. So the number of hidden layers will be more than 2. It could be 3, 4, or tens or hundreds. Okay. Then there is one more key principle or concept that is called the gradient descent. Okay, we said that W and B, these are the weights that the neural network will figure out. These are the weights which will be there, or the parameters which are fed to the hidden layers W and B. And initially some random values will be fed into W and B, assigned to various W's and B's in the hidden layer. But what gradient descent does is, we say there is an input. We already know there is an input and there is a corresponding output that we know. Now we want this neural network to learn that for a certain input, what would be the output. Okay, that is what, for this input, this is going to be the output. That is what we want the neural network to learn. And for that, for the neural network to learn it properly, how do you test it? Uh, for that, we what is used is the concept that helps in coming up with the accurate prediction is the gradient descent. Okay, so what is done here is, it's a very simple thing. You start, these parameter values with any parameter value. Okay, take any parameter value, but you are going to nudge these values, and here j w comma b is the cost function. Cost function is like, the lower the cost function, higher is the accuracy of prediction. Okay, so we want this cost function, to be lowest or the minimum. Okay, so how do we get it? So that is where we make use of gradient descent. Start anywhere, but nudge the value of all these parameters to such an extent that the cost function is minimum and the accuracy, and as a result the accuracy of prediction is increased. Okay, so this is the objective of gradient descent, which is done. And what is the technique that is used for it is back propagation is what helps in performing gradient descent. Okay, and for finding the output, okay, for the given input, okay, this is going to be the output. The flow that happens from the input to the output layer, that is called the forward propagation. Okay. Right. Now there is also activation function that we saw. Okay, so there is going to be an activation function in these hidden layers. We saw the ReLU function, but there are different functions like sigmoid, tanh. These are different activation functions. Now the objective here is, based on the parameters or what we are predicting, say we get an input, it's not that all these neurons are going to be activated to get the output. Okay, so say if we want an output which is here, in this second output neuron, maybe in the first layer 2 neurons would be activated, maybe in the second layer 1 neuron would be activated, maybe third layer this neuron is activated, and then maybe here 3 neurons, and then we get the output. Okay, so what is the idea here is the neurons, to get the output, the neurons that fire together, they wire together. Okay, so there will be a connection between the activated neurons. Okay, so this activation function helps in, so depending upon the value of Z, and depending upon the threshold which is set for that particular activation function, only the values of Z that passes that threshold, only those neurons will be activated. Okay, and the neural network will learn this by trial and error. Okay, which neuron to be activated and to get the corresponding output. So by performing trial and errors, the neural network will find that. Okay, so these are the key concepts of deep learning. Okay, so we saw a single neuron neural network. Okay, where we just gave the area, and what we predicted is the market value. But in some in the real world application, it may not be so simple. So we have area as well as the age of the house. What is the type, whether it's an independent house or a flat, even that has it could have the influence on the market value. The location, whether it's a prime locality, that also decides the market value. So here, the input layer will have these 4 parameters. Okay, for So say, you have the data of 100 houses, okay, and for all those 100 houses you'll have these 4 parameters. So pass on these parameters, okay, and so now the here there are 2 hidden layers, okay. This is the first hidden layer, this is the second hidden layer, and then we have the output layer. The input layer is always counted as the 0th layer. So the neural network, the number of layers we count is always from the hidden layer. So this is a 3-layer neural network. Okay. In the first hidden layer, there are 6 neurons. In the second layer, there are 3 neurons, and the output has just 1 neuron because we have to get the value, okay, market value here, right? Okay, so these parameters would be fed into this neural network, okay, and we know the market value. So this neural network will now, each of these connections will have a weight, okay, and there will be a biasness associated with each of the neurons. Okay. So say, so the weight between these 2 layers would be the number of layers, neurons in this layer into the input. So that comes to somewhere around 24 parameters here, and there will be 6 bias here, okay, parameters in this layer. In the second layer, there will be 3 parameters, and then we have to get the market value. Okay. And as I said, depending upon the threshold, that is the bias value for each neuron, given a record, it's not that all the neurons will get activated. It's only based on the way, the parameters, the weights which are associated with it, only based on that, and the bias associated with it, whether it has crossed the threshold, those neurons will be activated, okay, to get the market value. Okay. So let us now take one example. Okay, this example has been, this is a neural network example. So there is this Pima Indians onset of diabetes data set, which was issued by UCI machine learning repository. It was available there. And it describes patient medical record data for Pima Indians and whether they had an onset of diabetes within 5 years. Okay, so these are the attributes which are there in the data sets. It is a CSV file, and the values are basically, they're all numeric values. Okay, so so we have 9 attributes, number of times pregnant, plasma glucose. These are the different parameters which are there. Body mass index, diabetes degree, age, and the 9th parameter is the Y. So the first 8 are the X, and the 9th is the Y, that is the class variable, and 0 stands for not diabetic, and 1 is for the diabetic. Okay, so this is so it is the prediction based on these parameters whether the person is diabetic or not. Okay. So what we have here is this. Okay. I have got this code with me. Okay, I hope it is visible. And here we are making use of NumPy is used. So this is NumPy is a package. It's a Python package, okay, which helps in organizing the data in different dimensions. So from NumPy, we are going to import, since it's a CSV file, the load.txt package is imported. Okay. Then from Keras, the model that we are going to draw is the sequential, or the model, the deep learning model, which is going to be, we are going to import as sequential, and it is going to be the dense layer, like where each neuron is connected to the other. There's a connection between the different neurons in different layers, okay, in the consecutive layers. Okay, so that is what is represented by dense. The first here is load this data set. Okay, so there are 9 attributes in this data set, and they're all numeric. We saw the different attributes. What is done here is split it into X and Y. So the first 8 attributes are taken as X, that is the input data set, and Y is the output data set, which is the prediction, whether diabetic or not. Okay. Now we are going to define because we are having this layered deep learning, layered neural network. So now we are kind of defining our model, deep learning model. So it is sequential. Okay. The first hidden layer will have 12 neurons. Okay, so it's a dense and 12 neurons. And the first hidden layer will have 8 inputs, right? We saw that there are 8 attributes in the input. So in the input layer, there are going to be 8 neurons. Okay, and the activation here is ReLU. The activation function used there is ReLU. In the next, that is the second hidden layer, is dense again, and it has 8 neurons, and the activation is ReLU. And the next layer where is going to be the output layer, and here we are not making use of ReLU, but we are going to make use of sigmoid. Why so? Because sigmoid gives binary value. Okay, we can get 0 or 1, so that is why we are making use of sigmoid here. Okay, so that is why in the output, because we want either 0 or 1. Okay. The next step here is to compile our model. So the loss here is calculated using binary cross entropy. Now all these details, we may not have the time to discuss them. Then the optimizer that we have is ADAM. So what is this ADAM optimizer will do? It is going to nudge the values of parameters W and B, so that the the cost function which reduces nudge them, such that the cost function is minimized and the accuracy of prediction is increased. And the matrix that we are interested in here is the accuracy. Okay. Now we are going to train the model. Okay, so we are going to, the method which is used for training the model is fit, called .fit. Pass the input, pass the output labels. Epochs here means how many iterations, how many times you want to train it. This is done to improve the accuracy. And the batch size here is 10, means after how many examples you want the cost function to get calculated. Okay. Once this model has been trained, okay, we are going to evaluate the accuracy of it. Okay, so dot evaluate will give the accuracy of this model. And the next thing that can be done is, once we know the accuracy, the next step is to make the predictions. Now predictions will be made where you know the X, but you want to predict the Y. Okay, so let us run this. Okay, see, you can see here that it has started training. Okay, the epochs, right? So 150 epochs. Okay, and we can see that the model has run 150 times. Okay, the accuracy of this model is 76.56. And then, we are passing some parameters. Now this is X. You can see here there are 8 attributes that have been passed to the model. And for these attributes, the prediction is 0, that it is not diabetic. Okay, the prediction here is 0, whereas the expected was 1. Okay, for these, the prediction is 0, something that was expected. For the third test data, the prediction is 1, and that is what was expected also. And for the other two also, what we expected is what the value that we have got. Okay, so these are the 5 elements of which 4 predictions are correct. So yeah, it's the accuracy here is almost around 76. The 80% accuracy is there for the prediction. Okay. So this is how we can make use of deep neural networks for making predictions. Okay, it's like learn means let uh, the algorithm knows what is X and what is Y, and it will figure out that, you know, how it will figure out, or it will set the in between layers parameters such that for a given X we can make the accurate prediction of Y. Okay, I hope it is clear. That is what we are doing. Okay, so this is what we can do with, you know, huge amount of text data. If we have text and numeric data, we have. Okay, but again, coming back to our problem that this is about the unstructured data, right? We have to worry about the unstructured data. Okay, so the unstructured data could be image, it could be text, it could be video. Okay, so one such problem which is there is the computer vision problem. Okay, so it is the, again, you know, I now here the predictions were like, okay, we had the data in text and we are making the predictions. Now here it's more like the computer will see something. Okay, the program will see something and it has to make the understand what it sees. Okay, so in a way, when the human sees something with their eyes, how they, you know, how they understand, you know, okay, this is a bottle, this is an apple. Okay, in the same way, even the computer should be able to understand the object, identify the object, classify the object. Okay, so the computer vision is the ability for a computer to see and understand what it sees in a similar way to humans. Image classification is one such application where, you know, there are different images, could be different images of cat, different images of dog, different images of rat, and, you know, you have to classify, okay, this is a image of a dog, this is the image of a cat, this is the image of a rat. Okay? So that is what is expected. Now the input is an image, and what we need as an output is that this is a cat or this is a dog, or we can even say, you know, there could be a binary classification whether the image has a cat or no cat. Okay, that can also be there. The more advanced computer vision problem is object detection. Okay, where you not only detect what is the object, whether there is a cat, you also need to localize that the cat in the image by making use of such rectangles. You can see these yellow rectangles. This is nothing but the localizing. So in this image, I want to identify the car and the traffic signal light. Okay, so it's not that, oh, there is a car. No, I need to detect there is a car, and I also need to localize it. Where in the image is the car? Where in the image is the traffic signal? Okay, so such techniques are also required. Okay, now if we saw the standard neural network, okay, let us see can that be applied, or we need a different version or the different flavor of neural network. Okay, so an image, we know it is a kind of a, you know, the image is captured in pixels. Okay, it's in the grid structure, say 64 cross 64 pixel image. So this is an example of a 64 cross 64 pixel image, right? A quite blurred image, and it can be represented using the matrix. Okay, the earlier example we saw, the value was already in the numerical form. Okay, now before the neural network processes an image, this image has to be represented in a numeric form. Okay, or for the algorithm to work, or the network to work. So what is done is that we take this 64 cross 64 pixel, and this is the matrix representation of it. Okay, so the matrix representation is 64 cross 64 cross 3, because it is, you know, classified into RGB channels. Okay, so we have 64 cross 64 cross 3. So this is these many. So the feature, and this is the feature extraction from this image. So the feature extraction is done in the form of this feature vector, okay, and the size of this feature vector is 64, sorry, 64 cross 64 cross 3, okay. So what does this mean is the values which will be here, say 8 is there, so it will come here, next 12, that would be the second row, then maybe 44 here, it would be the third row, and so on. So once we have put the pixel values of R, then we will start with the pixel value of G, then we will start with the pixel value of B, and all these values will be kept, these values will be kept in the form of feature vector of size 64 cross 64 cross 3, and this is the feature extraction, and this would now be the input to the neural network that we saw, okay. And then there will be hidden layers, and we are going to get the output, okay. So this is how a standard neural network would work, okay. Now here the image size is small, 64 cross 64 cross 3, so mostly this feature vector size is going to be, say, maybe 4,000 or 5,000 rows will be there in this feature vector. It would be 5,000 cross 1. Okay, but what if the size is 1,000 cross 1,000 pixel? So the clarity here is better than the previous picture. Okay, and the matrix representation is going to be 1,000 cross 1,000 cross 3. And when we put it in a feature vector, we are going to get this feature vector of size 3 million. Okay, 3 million, and this is going to be the input. And if we take this as an input to the standard neural network, then the parameters that it would require are going to be 3 million parameters. And training these parameters, or performing a gradient descent on such a huge number of parameters, it is going to be a cumbersome process, and which may not give us the desired output as well. Okay, so that is why we cannot use the standard neural network that we saw, the dense neural network that we saw for images. What we need here are convolutional neural network. Okay, so in a dense neural network, we had input layer, then there was hidden layer, where each layer, though the composition of the layers remains homogeneous, only the number of neurons in each layer would be different. In convolution neural network, we have different types of layers in the hidden part in between the input and the output, and these are the three types of layers. So we have the convolutional layer, we have the pooling layer, and then we have the fully connected layer. Okay, what convolutional layer does is it basically, there is this image, say this is a 6 cross 6 image, okay, and these are the pixel values, right? We can see that the three columns here have 10, and then here it's 0. So maybe the image has got some kind of an edge here. Okay, there is a contrast in the image at the midpoint. And what we do is we convolve this image with this 3 cross 3 filter. So what is done is this 3 cross 3 filter would be applied to the first 3 terms. And what we are going to do is we are going to find the dot product, okay, and of these parameters and these parameters, okay, and the value that we get out of performing, the summation on the dot product is going to be the value of the convolved feature here. Okay, so you take these values and you do a dot product here, and what you get is 0. Okay, take these 3. Okay, now move it, shift it by 1 cell. Okay, now this filter is going to be mapped here. Okay, so what we get here is uh, all these tens are intact. Okay, so we get 30, 10 plus 10 plus 10, 30, because multiplied by 1. Then these tens are multiplied by 0, so all 0. And these zeros multiplied by minus 1 are all 0. So the value that we get is 10 plus 10 plus 10, 30, and that is what comes here. Shift by one cell. Okay, so now this is going to be mapped here. Okay, and again we are going to get 30, and next is it's going to be mapped here. Okay, and we are going to get 0. The next, take these three, find the value, take this. So what we get here is 4 cross 4 convolve feature. So what we are doing in the convolutional layer is we are doing the feature extraction in the image. Okay, so convolution layer performs the feature extraction. Then there is this pooling layer. Okay, so now again this is the convolved feature, may not be having. So what we have detected here is, there is an edge. We have detected a horizontal edge here. So there is the vertical edge here, that there is an edge in the image. So this feature that we have detected is an edge. So we have used this filter to do the edge detection in this particular image. Okay. Now we get a convolved feature here, some feature, and what we do is in the pooling layer, again this is what we are doing here is max pool 2 cross 2 pixel. Okay, so take 2 cross 2 pixel here, and in max pool find the maximum of these 4 cells, which is 11. Stride of 2 means here the stride was of 1, means moved by only 1 cell. Here we said stride of 2 means now move by 2 cells. So we have now these 2 cross 2 pixel. The max of it is going to be 19. Again stride of 2. These pixels, what we get is 12. And from these, we are going to get the max pool as 18. The pooling layer is basically is used for down sampling. It is used for reducing the size of the size of the features that we have extracted. Okay, so the pooling layer basically it performs the downsampling of the information that we have. Not even the feature, the information that we have, we are doing the downsampling, and at the same time, the information won't get lost. Okay, the information will be there, but only what we are going to do is the downsampling, reducing the size. Okay, and then there are these fully connected layers. So, and what the fully connected layers does is they take the low-level features, we can say the simple features, and they can these fully connected layer can derive or extract the complex features, or combine these simple features to come up with a bit complex feature. Okay, the next layer will take that and it will come up with a combine the features, and they will so that we get the more complex features. Okay, so the convolution neural network looks like this. Okay, so you have so let us take an example here. The input is an image, and the output are these 4 labels. Okay, it could be say a ship, or it is a bird, or it is a what you can say, is it a plane, or is it a fish? Okay, so we are going to give the image, and what it does is it will give us the label which which of these 4 it is. Okay, so so image is the input, right? In terms of pixels. Now what conv1 will do is it is going to extract the features. Pool 1 is going to reduce down to the downsampling. Okay, now here we have 2 layers of conv and 2 layers of pool. Okay, now there could be convolution neural networks where there can be multiple conv and pool layers that could be there. Okay, now here we are applying the second convolution and the pool, and then we are going to apply the fully connected layers in the end, and now what we get is the output, and so here we are going to get the output here. Okay, and one minute. Right. So what is happening here is, as we said, this figure shows the features. So the first conv layer, or the pool con one and pool one, they're going to extract simple features. Now these simple features, it could be an edge, it could be a curve, right? Now from these edges and curves, the next layer are going to derive more complex features. So by connecting these features, the simple features, the next layer may find, okay, this is an eye, okay, this is the nose, this is the the mouth, ears, okay. And now combining these, okay, the next layer, what it will do is it is going to combine these features, and the final layers will be able to recognize the face. Okay, so this is how the convolutional neural network works. There is a feature extraction which starts from simple features, and it keeps building and builds the complex features. Okay, so again, if we take the example of say um, of a bird, maybe here you would identify some edges, then a beak of the bird, or the the tail of the bird, and then the next layer may show it as the bird, and we can make the prediction that, okay, this is the bird. Okay, so this is how the convolution neural network works. Okay, how they are used for image classification. Okay, now there are different you know different CNN algorithms, models which are available, like ResNet, there's this AlexNet, okay. Then nowadays we see a lot of object detection algorithms, like YOLO is there, which is used for object detection algorithm. So here I'm just try to explain, how this convolution neural network works. Right? Okay. So now we'll see one more example here. Okay. Now we'll see on one image classification example. Okay. We may not use the CNN here. Uh, why? Because our data set, here is the even the pixel size of the images and data set is 28 cross 28, so we may not need the CNN, and the objective here is to demonstrate the functionalities. So but yes, we have built the CNN models in our research activity in the agriculture domain, and we are in the process of publishing it. Okay. So how we can find, this? So there is a data set, fashion MNIST data set, which is there. Okay. So there are these 9 labels are there, right? And so the output will have these many neurons will be there in the output. Okay. This data set comprises of 60,000 images, and as I said, 28 cross 28, and these images could be of a dress, coat, sandal, and so on. So the input would be an image, and the output of this neural network should be the label. Which image is this? Is it a coat? Is it a sandal? Is it a shirt? Right? So let me. right, so here we have this, okay, so we are going to make use of Keras. Now, Keras is the package which helps in, defining our own models. And the Keras package, it can use different deep learning frameworks in the backend. TensorFlow is one such framework, okay, developed by Google. Then Theano is another such framework which can be used for developing, is also a deep learning framework. Then Microsoft CNTK is there, which is not which is not used quite frequently. But here we are making use of Keras, and we are going to use build this model in using TensorFlow platform. Okay, so what is done here is now the Keras has many data sets. So this fashion MNIST data is also there. So the training and test data. Okay, so we understand this that the model is trained using the training data and tested using the test data. So they are fetched from this data set which is available with Keras, and it is loaded. Okay, and what we see is that the train has the size of 60,000. Okay, and the test has some 10,000. So there are 60,000 images, and this is the pixel, 28 cross 28 pixel is there. Okay, and what we can do next is, and we can make use of matplotlib, okay, and we can plot and see which image it is. So let me run this and see. Okay, by the time it runs, we'll see this. And now, before, we have the train data set, x underscore train we have, and we have this y underscore train. Okay, so we said it is 28 cross 28. Now, before this training set is applied, it's a grayscale, we need to normalize it. Okay, so both the train and test pixel values will be normalized by dividing by 255. Okay, so now the values that we are going to get are going to be somewhere in between 0 and 1, which are going to be normalized values. Okay, now the Keras model sequential, and it is going to be dense. As I said, we are not going to build a CNN here, and flatten. Now what? So here now we have started, defining the model. It's sequential. Flatten, what it does is it is going to create the feature vector. Okay, so it is going to take this pixel 28 cross 28 image, and it is going to come up with the feature vector the way we saw in the slide. Okay, now this feature vector will now be applied. Okay, so this feature vector is going to be applied on a hidden layer. Okay, so the input will go to the hidden layer, which is has 200 neurons, and the activation is ReLU. And then we have an output which has 10 neurons, because we have 10 labels, 0 to 9, and the activation here is softmax. Now what softmax does is it takes the real values and it will give us the probability. Okay, it will give the corresponding probability distribution of the output. So so we are going to have these 10 neurons. Okay, and the neuron which has say 0.8, 0.7, 0.9, and the sum of all these 10 neurons, the probability of the sum of the probability of values which are there in all these 10 neurons is going to be 1. Okay, so say there is one neuron which has 0.7 probability value, so we are going to say, okay, this is the predicted value. So that is what softmax helps in. We get the predicted value. But in the beginning, before the training, since the parameters are random, even these softmax values are going to be random. And as we train the model, the parameters are nudged so that the cost function reduces. We are going to get the probability distribution as per the prediction. Okay. So now, if we give the summary of this model, the summary is that the input has flattened. So 28 cross 28, it gives 784. Then the in-between model has 200 into 784. So these many parameters. And then we have the output where we have 10 neurons are there. Okay. Compile. Okay. So again, specify the optimizer metric. Run the train and build the model by making use of fit method. So pass the training x train, y train, and how many epochs you want to run it. Okay, and once it is done, then we have to test. Okay, so now this has already been done. In the interest of time, the plot match show the first or the second test value is a this. Okay, we see this image is there. Okay, and if we want to make use of this and we want to make the prediction, right? So what we get here is the print yp2 value, or print the argument yp. So what we get here is the labels, of the corresponding index, okay, that has been predicted. Okay, so here 1 means it is the first label that has been fetched. Okay, and then one can even evaluate the model, and this is to evaluate the performance of the model. Okay. Let me see. Okay, so I'm just so here we are building the model. Hmm. Okay, so the this test is one is a t-shirt, and say if I want to find YP1, so I get 9.6 in the third value, which is this 012. This is the third, which is nothing but a pullover. And what we see here is a pullover. Okay, so that is why here the prediction value is a pullover. So this image is fed into the model, and we get the value as the pullover. Okay, now let us see the first test value, what it is. It is a shoe. Okay, and let us see what is the prediction for this what is the predicted label for it. So here 0 1 2 3 4 uh, 5 6 7. Okay. Okay, sorry, shoe means ankle boot. It is the ankle boot. 0, 1, 2, 3, 4, and the highest value that we get is for the ninth one, that is the 9.6, and the 0, 1, 2, 3, 4, ninth is the ankle boot. So yeah, this is a shoe which is nothing but the ankle boot. So this is how this code is helping us in um, doing the image classification. And we have not used CNN here, but we have made use of the dense or the standard neural network for the prediction. Okay. Now, okay, we saw that convolution neural network is the variation which is used for images. Okay, any kind of images, we make use of convolution neural network. The recurrent neural network, they are used wherever there is a sequential data. There's a sequence in the data, right? In a text, an adjective will come before the noun. There is a sequence. Temperature, okay, there is a sequence there, time series with respect to time. Movie, there is a sequence in the movie. So recurrent neural networks are used where there is a sequence which is involved. Okay, and why we need a recurrent neural network here? Since there is a sequence here, we need for any prediction, and we need to know the past values also for any kind of prediction when there is a sequence which is involved. In classification, all the class labels, they are independent of each other, but that is not the case in sequence. So the standard neural network, all the output, neurons, they're independent of each other. Whereas in the case of sequence data, there is a relationship between the sequence, okay, and this relationship needs to be captured, and that is why there is a need for recurrent neural network. Okay. The recurrent neural network, it will perform the same task for every element of a sequence, with the output being dependent on the previous computation. And one more, the key principle here is that they have a memory. So because they depend upon the past, they capture the state. So a neuron will capture its state and pass it on to the next neuron. Okay, so there is a memory which captures information from the previous computation nodes. So the computation is performed. So there are two inputs. One is the input for that particular state, okay, that particular time t, and then there is an input from the previous state. So be it speech, text, audio, we make use of RNN. Okay, so now this is the representation of RNN, right? So there is an input and there is an output. The S is nothing but the storage, the memory. Okay, and this, the loop shows that it is recurrent. It will be executed for the same step will be performed for all the elements. Okay, so this RNN, it will be unfolded depending upon the size of the input. So say we have a sentence, this is from the yesterday's News in Republic, that Didymos asteroid hitting Earth in 2022. Okay, so this is a sentence which has got 6 words. So the recurrent neural network will be unfolded and there are going to be 6 layers. Okay, so there are in each layer one word will be sent as an input. Now RNN can have different applications. It can be used for sentiment analysis. It can be used for price prediction. It can be used for predicting the missing values, right? Here we are making use of it for named entity recognition. So in this sentence, we are trying to find a named entity. Okay, so this is a trained RNN, and we have passed this sentence. Okay, and it has unfolded to 6 layers because there are 6 words in this sentence, and the output here is 1 if there is a named entity in that word, and one can even capture the start and end of the named entity, and 0 if there is no named entity. Now you may ask why this named entity recognition. Now this named entity recognition is used in various applications. It is used in various these knowledge dissemination sites or the news portal, where you see the news which are classified, or you can say, the news which are kind of grouped. News items are grouped with respect to a person, or with respect to a country, or with respect to a city, date, year, occasion, some event, right? So this here RNN helps in finding the named entity, and accordingly that particular text or the information will be grouped according to the named entity recognition algorithm. Okay, so the we'll see this, or maybe in the interest of time, let me move forward, because here what is there done is there are IMDb reviews are there, and the neural network is used for identifying the sentiment. Okay, so there will be a text input, and in that text input, the output is going to be the either whether it's a positive sentiment or it is a negative sentiment. Okay, so this is one example. Now, of late, we have seen this convergence of cloud, IoT, and big data. We are this convergence of IoT, cloud, and big data. It has created various ecosystems. We have different services which are spread across different geographic locations, and they kind of interlink with each other, or they orchestrate with each other in order to perform certain activity. So there are many such ecosystems which are there. Smart city is one such ecosystem. Okay, precision agriculture is another such ecosystem which is there. So these are the emerging and the contemporary applications that are developed as a result of these technologies. Okay, and so now we are having the need for such applications. Say in smart city, there's a need for surveillance. In cyber security, there is a need to for early detection of any attack. Then, in the case of self-driving cars, there is a need for another car. Now, the intelligence that is there so far, it is like, okay, classify, this is this. Okay, now we need a level beyond that, to build a layer beyond that, or keep this as a platform. We have to build one more layer over it. In case of self-driving cars, the car is going to have its own camera. It's going to detect the objects, the other car or pedestrian in the runtime, and it also has to navigate in an accurate manner. So it's not only detecting, but also coming up with or deciding on an action based on what the self-driving car has detected. So it's one more level of complex level of intelligence that is required now. In healthcare, yeah, a lot of advancements is happening in healthcare, where we make use of CNN. Basically, convolutional neural network is used on the various images, health images, to for the detection or prediction of any disease. Price prediction. This is something which we have worked on. Their RNN algorithms can be used, where you have these time series data, say stock market price, or we can say agriculture commodity price, and now you make use of the data which is there to make the prediction. What will be the market price after a week, or tomorrow, or in future? So the RNNs can be used for not only for NLP but for making such price predictions. We already have a publication on this. Then yeah, something which we are working on now is the precision agriculture, where AI ML techniques can be applied on the field data, and to generate various insights. It could be the disease detection, it could be pest detection, it could be the quality of crop quality. Okay, so this is these are also applications, where the big data which is being generated, we need the big data analytics here to come up with these applications which are not the conventional applications, but they have evolved as a result of these devices or cameras which have been mounted everywhere. And these applications, they bring their own set of challenges. There is a need for incremental learning. In case of IoT devices, there's an input data stream. So the algorithm has to, or the neural network needs to keep on learning. Okay, and there's a need for real-time data monitoring and analytics. Then there is also high dimensional data, the remote sensing data, images. So there is a high computation cost that is involved. So that is another challenge which needs to be addressed. Then large scale models, so extract more complicated features and representations. So as the model size or the neural network size grows, there is a need to extract more complicated features from them. So such challenges also needs to be addressed. Then something that we are hearing these days of algorithmic biasness. Now we want to replace the human intelligence with artificial intelligence. Brain intelligence with artificial intelligence. Now the humans can feel. The humans can feel. The machine cannot feel. So now, how do make a machine learn, know that something has gone wrong, because the machine cannot feel. So that is something which is being taken care of by algorithmic biasness. So detect and mitigate them, that there shouldn't be any biasness in the model. So the data and the model should be right. Then there is also need for security and privacy, which is something which is of my research interest. And the data can be there in different, distributed environment. Now, how do you apply, maybe because of, say, the healthcare industry, due to the sensitive nature of the data, the healthcare providers or the hospitals may not be ready to share their data. They will say, okay, you analyze, but you don't share this data. You analyze in such a way that you just get to see your result and nothing else. Okay, you can club it with other the results of other hospitals, but the other hospitals shouldn't know the data, the patient data which is there in my hospital. So how these such models can be built in such a distributed environment in a security and privacy preserving manner. So these are the challenges which needs to be addressed. Then the development platforms, Keras, TensorFlow. Okay. Then there's this PyTorch, Theano. Then the Spark has got its mlib package. Python has matplotlib for visualizations, scikit-learn for machine learning algorithms, Pandas, SkyPy, NumPy. Now these are the different platforms which are available for coming up with deep learning, building your deep learning models. So deep learning has catalyzed the mutualistic relationship between AI and big data. Okay, so it is the big data, deep learning, which has we can say it has emerged out of it. The relationship between the developments that have happened in AI and big data field. It has enabled a creation of economic, business, and societal value out of big data. So it is the deep learning algorithms, which in fact, which have helped in deriving novel insights from big data. Deep learning algorithms and architectures are more aptly suited to address issues related to volume and variety. That is what we saw, huge volumes of data and variety, unstructured data. Okay. The emergence of ecosystems due to convergence of IoT, big data and cloud have created big data analytics opportunities and challenges. Okay. So we need faster algorithms. We need scalable algorithms, and the deep learning researchers need to address several of these challenges. In order to perform such um, analysis. So, thank you. With this, come to the end of the session.
Yes, thank you, ma'am. Ma'am, we have one question from a participant. Shall I read it?
Yeah, sure.
Yeah. So the question is how to decide whether the patient is diabetic or not, and what parameters we can consider.
Okay. Now, in the study, we saw, some 8, 9 parameters were considered in this particular study, the data set that we saw. Here, there is always a need of a domain expert in developing the AI model. So the data would be there, but there's also a need of a domain expert who could be a physician or a doctor who can help in identifying which are the parameters which are required for detecting.
Okay. Yes, ma'am. I hope the one who asked the question may be satisfied with the answer, and me like go for the study with the expertise in the field. And yes, the participant replied that he got the answer. Thank you so much, ma'am.
Yeah.
And here we can conclude the session. On behalf of entire organizing team of the program, I extend my sincere thanks to ma'am. Thank you, ma'am, for accepting our invitation and being with us and presenting such a nice technical session. So thank you once again, ma'am. It was indeed a very nice and technical session.
You're welcome, and thanks for giving me this opportunity. Thank you very
Yes.
much.
Yes, thank you, ma'am. Thank you so much. Yes. So, dear participants, here I declare the end of day one of the program. Stay connected on the WhatsApp group for the updates for day two. Thank you all. Have a nice day. Thank you.
Thank you. Thank you.
Thank you.